So let us start lecture 22. In the previous lecture, we finished the discussion on the time dependent perturbation due to a constant perturbation which is applied at some time t equal to 0. So before t equal to 0, the system was described by some Hamiltonian H0 which is completely known, and afterwards there is a constant perturbation which we had denoted by V, and the result that you had obtained was basically the Fermi's golden rule. If the transition is from some discrete initial state to some state which is the state which is lying in the continuum, so that gave us the transition rate or the probability of going from the initial state to the final state per unit time, which we call the rate of transition, and this was given by Fermi's golden rule. So next thing that we wanted to discuss was the same calculation, but now we have some harmonic perturbation. Earlier, remember, our time dependence actually entered the calculation because we had said that after a certain time the system is being perturbed by constant potential. So in that manner, time dependence entered in our calculation. But here, from the very beginning, we say that this H0 is already known, but H prime has already a time dependence which is harmonic. So our total Hamiltonian, which we denote by H as a function of t, is a combination of H naught plus H prime, where H prime of t has this particular form which is 2H prime cosine omega t, and this is true for a range which is this. That means the time which lies between 0 and t0. That means my perturbation is switched on for a time t0. That's what is the meaning of this thing. And for t less than equal to 0, there is no perturbation. The system is described by only H naught. So here I understood when I discussed this thing in the class that it probably would have been better if I had used a different symbol for this H prime. What I really wanted to mean here by using the same symbol as this H prime is that whatever perturbation you are actually having, the time dependence part has been taken out, and rest, which is not dependent on time, is being discussed or it is being denoted by H prime. So this H prime which is there on the right hand side is not the same as this which is there in the left hand side. So H prime, this quantity, is time independent. At a later stage I had used a calligraphic H prime instead of this H prime just to avoid confusion. Okay, so now we are looking into this type of perturbation, and we are looking into a range where our omega is always greater than 0. Now if you recall that all this thing started with writing this psi tilde ket as sum over Cnt, and then this ket n, which were the eigenstate of the unperturbed Hamiltonian H naught. And from there we had seen that how to write down the coefficients, the first order perturbation in perturbation theory, how to write down these CMs. So if we keep terms only up to first order in this expansion, then we had already seen that I can write this Cm1t as this integral. So this we had discussed long back. So this result is going to be with us throughout this discussion of time dependent perturbation theory. The only thing that changes are sitting here in this form of this perturbation. But we also know the same argument we had used in the case of constant perturbation just in the previous day's class, that suppose here my n is the initial state. So at time t equal to 0, I start with a state or with a system which is having the initial state which I denote by ket I. and therefore we will always take Cn0, which is lying on the right hand side of this equation, to be equal to delta Ni, which tells me that at t equal to 0 there cannot be any other state, it's just n is equal to I. So wherever I find any n, I will replace with I. And for a transition to the final state, which I denote by ket f, at some time t0, we will definitely going to take or definitely going to replace all m's that are sitting here by f. So therefore, as you can see, I have already replaced this m by f, and then I will have everything e to the I f omega fi t prime, where m and n are being replaced because this Cn0 has been replaced by delta Ni, and also there is a summation over n. So the summation over n will obviously go away if I replace Cn0 by delta Ni. That delta Ni, the Kronecker delta, is telling me that my n should be equal to I, and then only this sum will go away, and the sum you can see is no longer here. So 1 by I h bar I have taken out, and whatever rest is there, I simply write it as h prime fi, and which is a function of t prime, and the integral obviously is over dt prime. And as you know, I have already said the perturbation is acting there for a duration t0. The integration limit is from 0 to t0. So now I simply replace this h prime fi, which is a function of t prime, by the form of the perturbation, which is 2h prime cosine omega t, where h prime is some function which is time independent. So I replace this 2h prime fi cosine omega t prime, and then I do this integration, which is very easy to do simply because this cosine omega t prime I can break as e to the I omega t prime plus e to the minus I omega t prime divided by 2. In fact, you can immediately see the importance of this factor 2, which I said is just a convention. This factor of 2, which is there in this h prime of t, you could have simply started with h prime cosine omega t, just have forgotten about this 2. Then also you would have got the result, but then it would not match with the Fermi's golden rule that you have already obtained for constant perturbation. So that would differ by a factor of 2. That is why writing your perturbation form in this way actually is helpful. Now, as you can see that this h prime fi, I have said that is time independent, therefore this h prime fi goes out of the integral, and here you will have e to the I omega fi t prime and then e to the I omega t prime. So that will give you e to the I omega fi plus omega t prime. Similarly, the next term will be e to the I omega fi minus omega t prime. And this integration is very easy to do, it's just exponential function, so you know what the answer of this integration is. You just do this integration and then finally you put the limits. The result that you obtain is written in equation 77. That's very easy to figure out. Now I have few comments to make about this result. As such, in this particular form of this Cn1t, it is not very useful simply because there are these two terms, and at the moment it seems that these two terms, I do not know what to do with these two terms. I do not know which of the terms is important in our calculation, whether we should look for both the terms, whether some limit exists or some point exists when one of the terms is more important than the other term. So all these things we will discuss now. Now, as you can see that by our definition, omega fi is defined as Ef minus Ei by h bar. So, if by some means I can find out what is the final discrete state energy Ef, then I can figure out what this omega fi is. This is simply because Ei, or the initial state energy, is already known. Why it is already known? Because our initial state I is a stationary state. you remember we started with the Hamiltonian, which is the known Hamiltonian H0. Initially at the time t equal to 0, I had the Hamiltonian H0 which is known completely. That means whose energy eigenvalues as well as the eigenfunctions are already known. Therefore, this state ket I is one of the stationary states and that is basically known to us. So the corresponding energy is known to us. So if by some means I know what is this EF, then my omega Fi is known. The next thing to look at is that the amplitude that we have here, it basically is a form of a factor multiplying the sum of these two terms. You look at these two terms, it is just multiplying this factor h prime Fi by Planck's constant. So one of the ways to look at different limits is that you actually look for what happens when your T0 is very small, when is your T0 very large. You can look for those kind of limits. Now if you look for the limit T0 going to 0, suppose we are looking at the limit T0 going to 0 into this expression, then immediately you know that this is this object e to the I omega Fi plus omega T0 is of the form e to the I theta, where theta is omega Fi plus omega times T0. Now this omega, this e to the I theta, we can obviously expand as 1 plus I theta whole square by 2 like this. But then your theta is having this multiplicative factor of T0 and T0 is very small, T0 almost goes to 0. So therefore I can safely ignore these terms. So e to the power I theta should only contain the first two terms. And this one will therefore cancel with this one. So what will remain here is just I omega Fi plus omega times T0 in the numerator. But that omega Fi plus omega by should get cancelled with the omega Fi plus omega in the denominator. So this term will also have a factor of IT0. This term will also have the factor of IT0 in the limit T0 going to 0. So in the limit T0 going to 0, both these terms will give you the same contribution. However, you have to remember that we are actually interested in finite T0. That means my perturbation h prime of t has been acted on the system for a finite time T0. So at finite time T0, you look at the numerator of these expressions. The numerator has these terms, which is basically a complex number of some bounded absolute value that actually oscillates in time, because you can always write this thing in terms of the sines and cosines. Now if this is basically periodic, that means this value is basically bounded within some limit. It's a periodic function, it has some maxima, some minima. If it is just sine function, then the maximum and minimum value are actually within plus and minus 1. So therefore this thing for a finite T0, basically each numerator is a complex number of some bounded absolute value, which of course oscillates in time. Now as I said, these two terms are not relevant for us at the simultaneous point of time. At the same time, these two terms cannot be relevant for us. For example, this term is not relevant when omega Fi is very close to omega. If omega Fi is very close to omega, that means this object omega Fi minus omega is equal to 0 or almost equal to 0, then this term is no longer dominant. The dominant term is this one. Similarly, you also have a scenario when your omega Fi plus omega is very close to 0. That means omega Fi is close to minus omega. That point of time, your this term will no longer be of much importance. So suppose let us for the time being say that the first term is very relevant, first term is a very dominant term in this above expression of C and T, then omega Fi plus omega equal to 0 means I know what omega Fi is. Omega Fi is Ef minus Ei by h bar. So I simply replace that and what I get is this. That means Ef can be written as Ei minus h bar omega. That means my EF, the final energy, is basically lower than the initial energy. So if I look at the energy scale, then if the energy increases in this y direction, then EI is here, EF is below, and the difference between them is given by h bar omega. This condition is known as stimulated emission. What happens there? Here energy h bar omega is being released by some process, and this process happened to occur simply because we have perturbed the system. So because of the perturbation, we have some energy which is being released in a process. The process is known as stimulated emission. What happens here is that some photon comes, it basically lowers the excited state atom to some lower state, and as a result some other photon is also released. I will come to a pictorial description of this thing soon. Now when I say that the second term is relevant, that means my omega Fi minus omega is very close to 0, then there is no importance of the first term. That means omega Fi minus omega equal to 0 means Ef minus Ei minus h bar omega equal to 0. Therefore Ef is nothing but Ei plus h bar omega. So in the energy scale, we have Ei which is below, Ef which is higher energy, and we have the energy difference to be h bar omega. Of course, the process is known as absorption. It's simply because the perturbation is capable of giving the system some energy h bar omega to enable some transition between the I to F state, or the initial to final state. So that means energy is being absorbed by the system, by the atom in some level, some state, and by absorbing the energy it actually goes to some higher level, and that process is known as the absorption process. So we are actually having two different processes here. One is known as absorption, another one is known as stimulated emission. Now both the stimulated emission and absorption, they are important, and we will basically here in this discussion calculate everything corresponding to absorption. That means we will calculate this quantity Cf T0 up to first order in perturbation theory, whose general form we have already obtained, which is this. For the case of absorption, the stimulated emission can similarly be obtained by keeping the relevant term in this expression. Now for absorption, among these two terms, I immediately know that the second term is important, it dominates, therefore I can neglect the first term here, and therefore Cf1 T0, the perturbation up the coefficient of expansion up to first order in perturbation theory, it can be written as your omega Fi minus omega remains, but this quantity you use the same trick that you had used in case of the constant perturbation. That means you write this e to the I omega Fi minus omega T naught by 2, and then you will have a term like e to the plus I omega Fi minus omega T naught by 2, which will make sure that the first term is there, and then the second term is minus e to the minus I omega Fi minus omega T naught by 2. That will in fact take care of this factor of 1. So this you immediately figure out that this quantity is nothing but 2I times sine omega Fi minus omega T naught by 2. So that is what I have written here, and this thing is already there, that e to the I omega Fi minus omega T naught by 2, which is just a phase. And you know the probability of transition from I to F, when the perturbation is being applied for a time t naught is already, you know that this is nothing but the mod square of this CF1 T0, and since this is a phase, this will no longer be there, so I will have this 2 will give me 4 mod HFI prime square by H bar square, and then sine square of this thing divided by omega Fi minus omega whole square. So this is the transition probability that a particle which started out in the state I at time t equal to 0 when there is no perturbation, this system will be found at time t equal to t0 in the state ket f. So the probability, transition probability, is being given by this. Again, exactly same as the expression that we had obtained in case of constant perturbation. So if you look at this plot, you immediately know that this is this oscillatory behavior which you are looking at here in this plot. All this thing actually reaches 0, and looking at this expression, the amplitude is being given by this quantity which is written here. So this is the maximum value that this oscillatory function can reach, and the transition probability is exactly the same, as I already have mentioned, as that for the constant perturbation. The only difference is that the case of constant perturbation, we had, instead of h prime of Fi, we had Vfi, and instead of omega Fi minus omega whole square, we only had omega Fi square here. Similarly, here also we had sine square omega Fi t naught by 2. Why there is this extra omega? Because my perturbation itself is driven by this frequency omega. So that is why there is this omega Fi minus omega, and interesting things happen when omega Fi is near to omega, that is near the resonance frequency. So we already observed this, that the transition probability oscillates sinusoidally as a function of time, and then it basically reaches a maxima which is given by this value. And of course, this value needs to be very smaller than or very, very less than 1. Otherwise, the basic assumption with which we had started our calculation, that the perturbation is small, that will be violated, that will be invalid. Therefore, this has to be very small, this has to be much, much less than 1. And also you note one thing, exactly the similar way as in case of constant perturbation, the zeros actually occur as 2 pi by omega Fi minus omega, 4 pi by omega Fi minus omega. Earlier, in case of constant perturbation, this omega was not there, so it was just 2 pi by omega Fi. But now that our frequency is this omega Fi minus omega, so Tn, the zeros of this oscillatory function, will occur as 2n pi by omega Fi minus omega, where n can take values 1, 2, 3. So that means there is a interesting conclusion that you can make from here, is that the particle actually is certain to be back in the lower state. It is not that once it goes high, goes to the upper state, it will not come back. It will definitely come back, and you know the time by which it has to come back to 0. So that means the probability of finding the state or the atom in the higher state will become 0 at these points of time. Now, therefore, you can also conclude one thing, that if suppose now you want to maximize the chance of provoking a transition, that means you know that you need a transition from initial to some final state, and you do not want that final state to again come down to the initial state. So that means you should not keep the perturbation on for a long time. So you will get a better result if you only turn on the perturbation for a time duration of pi by omega Fi minus omega, which is half of this thing. If you take half of this time, then you are certain that this state is somewhere here. So that is another interesting feature of this perturbation. Now, of course, you know that our final state may be discrete, and if there is a final state may be continuous, it may be a part of a continuum, and if it is a part of a continuum, then you know that we have to sum over all final states. If you do the sum over all final states, but your energy levels or you are part of a continuum, that means you are no longer having discrete energies, then of course this integration has to be replaced by the the summation has to be replaced by the integration. And you know already how to do that, because you have to have some integral with some function of momenta sitting here, and then you will have the density of states within the energy range DEF. So that is what was the prescription which I had given to you in one of the earlier classes. Now you know everything in this expression. You have this result of Pi2F T naught, which is nothing but this expression. And then you have rho EF times DEF. But this time you also know that the main contribution, unlike the previous case where you just had omega Fi, there was no omega in the constant perturbation case. Here the main contribution should come from this interval omega Fi minus omega lying between 2 pi by T0 and minus 2 pi by T0. That is what is expected. So from here you can also see that this T0 should be 2 pi by omega Fi minus omega. So omega Fi minus omega should be 2 pi by T0. And that is what you are actually looking at, that interval. So the same argument which you had given in case of constant perturbation actually holds good in this case also, with the only difference being there you had only omega Fi, but here you have omega Fi minus omega. Everything else is the same. So similarly here also you replace this omega Fi by EF minus EI by H bar, and you do this calculation and you figure out what should be the range of the final state energy such that you have a good enough contribution from this range, the main contribution from this range. So for sufficiently large T0, this can be shown to be the narrow band of states, which is already shown to you in the case of constant perturbation. So here you look that this is your final state energy, and then you have a range of energies within this continuum from minus delta EF to some plus delta EF within this range, and that means the width of this thing is 4 pi H bar by T0, and here is somewhere your EI, so it takes some value H bar omega and reaches here, and in the absorption process we therefore have to integrate over a narrow band of states about the final energy EF, which is nothing but EI plus H bar omega. Now again the same argument that we had given in case of constant perturbation holds. I have told this many times. Now instead of being monotonous, you can simply say, like the previous case, we can take this rho EF out of the integral, we can take this H prime Fi mod square out of the integral by simply assuming that since the main contribution comes from a narrow band, within that narrow band there is not any sufficient change in this H prime Fi and rho EF. So by that argument you can take these things outside your integration sign, and whatever remains is very easily integrable. So you have this quantity which you call u, and then you figure out what is du, and of course your integration limit is from minus to plus infinity, simply because even if there are states near minus infinity, that is not going to contribute to your whole integration, because the main contribution, as you have seen, comes from this peak which is near the omega Fi equal to omega frequency. So So you do this integration, this result you already know what it is, sine square u by u square d from minus to plus infinity, this gives you pi. And because of this change of variables, there will be these factors of 4 by t naught square here, 2 by t naught here, and everything taken care of, you get this result that if you do the sum over the final states, this result that you obtain is 2 pi by h bar h prime fi mod square. Remember, this h prime fi is not the time dependent h prime fi, this is rather the time independent h prime fi, and then rho ef, and you know that this ef is nothing but ei plus h bar omega, and then there is your t0. Therefore, the transition rate again in this case, the probability of transition per unit time, that means dp dt or dp I to f t0 dt, if you calculate, this will go away. So in case of spontaneous emission, the only change that will occur in this formula, which we call the Fermi's golden rule for harmonic perturbations, is exactly same. If you look back, if you go back to your calculation for constant perturbations, you can see everything is the same here also. Here you had written down this quantity. Only difference is that here your EF was very close to EI, that is why we have changed this to EI, but then in our case we will have EI plus h bar omega, and of course there we have VFI mod square. Here in our case we will have h prime fi mod square. So this is the difference between the Fermi's golden rule when you have constant perturbation and when you have harmonic perturbation. And in case of spontaneous emission, as I said, you only change this formula which I have written here. There you replace EF by EI minus h bar omega. So let me stop here for a second and let me tell you that the main calculational part, which involves the calculation of Fermi's golden rule using or introducing the interaction picture, we had calculated how to figure out the transition probabilities when there is a time dependent perturbation, and then we have derived the Fermi's golden rule for two different cases, one for constant perturbation, two for the perturbation due to harmonic change in the Hamiltonian, that means there is a periodic change in the Hamiltonian with time. And we have come to the formal end of this part, but of course the chapter does not end. We have to do the application part now, and in the application part I thought of discussing the interaction of lights and atoms. Of course this is a part of the syllabus, but it is shown in the syllabus as a separate topic, but I would prefer to discuss this thing in this particular section itself, because what I find is that if I discuss this together with the time dependent perturbation, then it's kind of fresh and you can simply appreciate the results that we are going to obtain in this section. So what is the statement of the problem? The statement of the problem is the following. We are trying to solve a system which is a collection of atoms, and these atoms are having the possible energy levels, which is having these possible energy levels which are 2 in number, and they are interacting with light at some finite temperature T. So let me state this again to make you understand how complicated now the system has become. Firstly, so far we were talking about a single atom. So far we have talked about a single atom. But now I am suddenly saying that we have a collection of atoms. These atoms are having two possible energy levels. Now, as if the number of atoms becoming multiple instead of a single atom is not complicated enough, on top of that we have actually introduced the interaction of these atoms with light. By light, I simply mean electromagnetic wave. It can have any frequency. This light can be visible light, this light can be ultraviolet light, this light can be infrared light, this light can be X-ray, whatever. And as if that interaction is also not sufficient, we have on top of that introduced a temperature T also. So our life is already much more complicated than you can think of. So now the interaction of atoms with electromagnetic wave is happening at thermal equilibrium, suppose. So we are assuming that all these interactions are happening when there is thermal equilibrium. There is no exchange of energy, thermal energy, everything is in equilibrium. Now, as I said, there are two possible energy levels. I am denoting them by Ket A and Ket B. So Ket A, this energy level, the atom, when they are placed in this energy level or when they are in this energy level, they all have energies EA. If the atoms or the electrons in the atoms are in this state B, they are having energies EB. And we can always define this omega BA to be EB minus EA by H bar, and we assume that EB is greater than EA. Now you ask the question, what happens to this atom when one shines light with frequency omega BA? So there are a lot of atoms and we shine light with the frequency dA. So here let me very briefly tell you why this issue comes up. So Einstein actually considered some equilibrium state between the walls of an enclosed cavity. And suppose inside that enclosed cavity we have some radiation field, some light with some frequency, and atoms in the wall, they are constantly exchanging energies with the radiation field. The excited states of these atoms of the wall, they are very, very closely spaced, and essentially you can think of these spacings to be such that everything is in a continuum. You can think of that. So we consider therefore that the two states which we denote by Ket A and Ket B, and whose energies are also known EAs and EB, they are representatives of this continuum. So pictorially it looks something like this. So suppose this is a continuum, there are a lot of states in this continuum, and these Ket B and Ket A and Ket B, they are kind of representatives of the states in this continuum. Now there can be two possibilities that can happen under this scenario. One is that I can start with the system, the atom, where the atom is in the state B, which is a higher excited state, having some energy EB which is greater than EA. So atoms may actually transit from state B to state A. It may decay from state B to state A by releasing some photon, which I have shown here, by releasing some photon. So that means you start with a system where the atom is in a higher level, but then you interact with some photon. As a result, the higher level atom actually comes down to some lower level, which we denote by Ket A, and another photon is being released, which is shown here. Similarly, one can actually have the atoms from the state A going to state B by actually absorbing some photon. That can also happen. So here I have written that the electron, suppose, is in level A, which is the lower energy level. Therefore, absorption of the photon happens and the electron goes to the higher excited state denoted by Ket B. And as I said already, that electron, suppose, is initially in state Ket B, and there what you have is stimulated emission. That means the photon field stimulates an electronic transition from B to state A with the release of another photon. So that is very important. You have one photon and it comes to some higher excited level. It basically takes the higher excited level atom to some lower excited state, but then there is another photon which actually is released because of that. So I have drawn some pictures here. Suppose we are here before, so or before applying the photon or putting the light or shining the light on the atoms. So some h bar omega Ba actually falls on this. So this actually gets some energy h bar omega Ba, and therefore it transit to higher excited state, which is shown in the next picture where I have looked at what happens afterwards. This process, as I said already many times, is known as absorption. On the other hand, suppose I have already some atom which is in the higher excited state, which I denote by B. One photon comes, interacts with this, and then it actually takes it down to the lower energy or lower excited level. So that means when this actually comes down, it also releases a photon. So you have two photons now. One is the original initial photon with which you had started, and the other one is the photon which actually is released because of this stimulated emission, because of this object, because of this incidence. Now I would like to comment something about the rate of transition. So as you can see that the rate at which this higher excited state B decays into the lower excited state A is basically by our normal argument should be proportional to the number of atoms in B that are there in state B. And also it should depend on the number of photons of frequency omega in the radiation field with which the atoms are getting involved with. Okay, so this number of photon that I have just said, which is interacting with the atoms of the wall of the cavity, that is proportional to the photon energy density, which throughout our lecture we will use this notation U omega. So therefore, at this moment, you can actually talk about the transition rate of decay from B to A. So you are actually looking at this process and you are trying to figure out what is the transition rate of decay or of transition from state B to state A. For this process, you can actually think of WBA, as I said, to be proportional to NB. It can be proportional to the number of photons with which it is interacting, and then this BBA can be thought of as a proportionality constant, which Einstein named as some B coefficient. It's just some naming. Similarly, the rate at which the state A can actually absorb a photon and it can be excited to state B should be proportional to the number of atoms, which is denoted by Na, number of atoms Na which is sitting in the state A, and of course the number of photons of frequency omega, and that is proportional to the photon energy density, which is U omega. Now therefore the rate, I can always write it as a product of U omega Na and then BAB, which is of course not at the moment not same as BBA. It is some another proportionality constant, but later on we will see that this BAB actually is same as BBA. Now at the moment, since I have introduced the idea of stimulated emission, let me also very briefly tell you about laser. Laser means light amplification by stimulated emission of radiation. So if you take all the first letters of this sentence or this phrase, then you can see that you will get laser. Okay, so that is what the full form of laser is. Now, in case of stimulated emission, you know that the electromagnetic field gains energy, and that energy you can think of it to be h bar omega from the atom, and one photon went in and two photons came out. The original one, which actually caused the transition, plus another one from the transition that is happening there from higher excited state to lower excited state. So that means you started with a photon, and after this stimulated emission has happened, you have double number of photons. So this therefore basically raises the possibility of amplification, because suppose I have a lot of atoms, and suppose by some procedure, some mechanism, I am able to put all of them in the upper state, and I trigger it with a single photon, trigger the system with a single photon now, and therefore what I will expect that a chain reaction should occur. With the first photon, it will actually produce two more photons. These two more photons will actually produce four more photons, and so on. Therefore, we will have an enormous number of photons which should come out. Now, this enormous number of photons that will come out of this spontaneous, of the stimulated emission, they will all be having the same frequency, and they will always come out more or less virtually at the same instant of time. So this is roughly the principle behind the laser. Of course, you have to understand this fact that for the laser action to hold, you always have to have the majority of the atoms in the upper state, which itself is a very hard job to do, and this is known as population inversion. So you will ask, how can I actually do population inversion, or in other words, how can I put so many atoms in the higher excited state? So the method by which it is done is known as optical pumping. Of course, we cannot go into the engineering details of these processes, but roughly speaking, what happens here is the following, that there is typically a third level where the electrons are basically pumped using this optical pumping action. So once these atoms, which are all in the lower energy state, are excited to some third energy state, then it is the property of these levels, I mean like the property of the, in fact the, I should say the material or the atoms, that will tell you how long these atoms will be there in this state. So depending on the choice of atom, this third level can actually quickly send these excited atoms back to level B, which we call our level B, as the level B that I have shown here in these cases. Okay, so this state actually is known as the metastable state, and from here to here we can have these transitions, and thereby we can have photons coming out of this process. So pictorially, the laser action can be thought of as like this. There is one atom in the higher excited state, the state B. Let me write that. And this is our state A. And then one photon, single photon comes. It actually releases two photons. These two photons, which actually act on these two, they actually release 4. These 4, when they act on these 4, actually will release 8. So that is how the laser works. Now Einstein tried to give some argument behind this. So this part is a very tricky part. So what he said is that, like, we have this initial picture where I have a initial state, I have a state which is A, I have another state which is B, the energies are fixed, EA and EB, and there are Nb number of atoms in state B, there are Na number of atoms in state A. And of course, atoms in state A or B with Eb greater than Ea and with populations which I denoted by Na and Nb respectively, we know that the atoms are in equilibrium with the photon, and this photon is basically at some finite temperature T. Therefore, you can actually define the inverse temperature, which you already is familiar with. I am sure that you all are taking the statistical mechanics course. So from there, this beta, which is 1 by kBt, is already known to you. Now I want to make some observations. Firstly, the important observations are the following, that populations are actually in equilibrium. That means if I have n number of atoms in state A and if I have Nb number of atoms in state B, then I will assume that in equilibrium the number of atoms are not changing. That means with time Na and Nb is not changing, and that means Na dot and Nb dot should be 0. Now, I also want to claim at the moment is that the equilibrium that I am talking about is basically some kind of a thermal equilibrium. And you know that in the thermal equilibrium, we can actually write down this relation Nb by Na. It should be e to the minus beta Eb by e to the minus beta Ea. And therefore, you can write this as e to the minus beta Eb minus Ea, but Eb minus Ea is nothing but h bar omega Ab or omega Ba. And the third important point is that you all have learned black body radiation in your heat and thermodynamics course. The energy U omega d omega per unit volume of the frequency range d omega. You already know the Planck's black body formula. It is exactly the same Planck's black body formula that you can get here. It's h cross by pi square c cube, and then you have this omega cube d omega by e to the beta h bar omega minus 1. Now, as I already have said, what are the possible processes here? One is absorption, where the atom actually jumps from state A to state B. Another one is stimulated emission, where it is actually a jump from B to A. And as I also have said that the rate is already given by BAB U omega Ba times Na, where Na is the number of atoms in the state A, U omega Ba is the number of photons that is available, and this BAB, as I already have said, is a constant of proportionality, which is basically the known as the B coefficient that we want to figure out. Similarly, this BBA is also another coefficient. Everything else is the same. Now, when I look at this expression, I clearly see that this Na is sitting here. So, if I look at these two terms, this product, then it tells me that this gives us the transition rate per atom. That is also another useful quantity. Now, we have also said that the rate of absorption will be proportional to the number of atoms available in the ground state or the lower excited state, which is denoted by Na. So, it is capable of absorbing a photon, and it will also depend on the number of photons available, which I have denoted by U omega Ab, and also on the B coefficient. And you can already show that the same kind of arguments actually hold true for stimulated emission also. Now, the main question is, with this scenario, with these so many items at hand, can we achieve equilibrium? So, therefore, to understand this, let us actually look at the rate of change of Nb or Na, Nb and Na. Sorry, I think I have, no, it's okay. Let us look at this change of Nb. That means we should look at Nb dot. And as we have said that there is no change of number of atoms in the equilibrium, I will expect that NB dot, if evaluated, should actually be 0. Now what is NB dot? NB dot, I know that I have to have equal to 0 at equilibrium, but NB dot is also nothing but the rate of change of the rate of absorption minus the rate of stimulated emission. And you know, you already have obtained the results of rate of absorption and rate of stimulated emission. Here you already have BAB UNA, and here you have BBA UNB. So BAB times NA, and here you have BBA times NB, and then you have U omega BA sitting here. But then you take NA common, it takes this thing NA out of the bracket, and then you have BAB minus BBA, and then NB by NA. But NB by NA on the very first day I have said is nothing but e to the minus beta h bar omega. We have already seen this also. And then your omega BA is there. Now, isn't this a very strange result? Because what does this tell us? Forget about this and this, just look at this expression. This has to be 0. In order to have equilibrium, this has to be 0. That is our equilibrium criteria. So that means the B coefficients actually depend on the electronic structure in the atom. That is what we know. And it is not dependent on the temperature T. Therefore, this cancellation is not possible for any arbitrary temperature. That is simply not possible. This equal to 0 is not possible. That means therefore the transition is in trouble. Also, you also have to note that the photon energy density, it is not featuring in the equilibrium condition. That means equilibrium is also not possible. So we are in some problem for which we really do not have the answer at the moment, and we will discuss the answer in the next class.